Welcome to the 7th lecture in the course Data Structures and Algorithms. So this is the final and the fourth part on the lecture series Algorithms and Analysis. Now the prerequisite to attend this lecture is you should have completed the lecture number 6 and tutorial number 1. Only then you can proceed with this particular lecture. Let's move on. The objective of this lecture is basically to understand the asymptotic analysis of algorithms, but the focus will be predominantly on the big O notation. So we'll try to gain deeper insight and visualization of the big O notation with various complexity classes. So the key concepts involved in this lecture are the big O notation, especially the complexity classes, which are quite popular. Then we'll have a visualization of the big O with the physical implication, in a way with the trial experimental results to corroborate the interpretation of big O with the theoretical formulation. So we'll try to get some insight into the big O asymptotic analysis through this lecture. To begin with, so let us try to understand the big O notation in detail. So the points, the highlight of big O notation is what is given on the left hand side. So basically we are not interested in the actual function that describes the time complexity, right? We are not interested to find whether it is say 10 n power 4 plus 50 n plus 50 so on. So we are not interested in the actual function, rather we are only interested in the complexity class of the function, something like order of n power 4. So we do not exactly bother whether it is 10 into n power 4 or 20 into n power 4. So we are just trying to get the complexity class like n power 4. So in this particular framework, we will ignore any constant overheads as well as the small factors, constant factors. So this big O notation will tell only the principal growth of the complexity function, right? As it is obvious, if you say n power 4 plus n square, we are going to just project n square, which means we are going to ignore that n power 2 there. So it is going to only talk about the principal growth of complexity function with respect to the problem size. And this big O notation is going to be something of the performance. It should tell about the performance of the algorithm, especially when the numbers are large. So when n increases, like theoretically or mathematically how we write that is when n tends to infinity. But of course practically n need not be infinite, but quite a large number. In case n becomes a large number, then that is where the big O notation comes into play in real sense. Now let us look into some of the complexity classes. Say the complexity classes are O of 1, right? So what you have there is the pronunciation. So it is O of 1, so you should pronounce it as O of 1. If it is O log 2, it is always the base to the logarithm is to the base 2. So it is O of log n. So that is how we pronounce it. Same way, O of log n, the logarithmic complexity. O of n, O of n log n. So then O of n squared, O of n cube, O of 2 to the n. That is how we pronounce. So these are some of the complexity classes. As you can see, they are increasing in order, where O of 1 is the lowest and O of 2 of n, 2 to the n, which is exponential complexity, is highest. So this is about various complexity classes that we are getting introduced. Now down the lecture, what we will be discussing is what is the significance of this order of 1, O of 1 or O of 2 to the n, and what is the physical implication, right? Let us try to get some more details about these complexity classes. Moving ahead. Now, as you can see that this big O notation is going to be used for the runtime complexity analysis, right? So it will give you an abstract measurement. And the important aspect about the big O notation is we don't require any mathematical proofs, rather we just want to say the complexity class. So even without the mathematical proofs, we can try to judge the runtime complexity with the help of big O notation. Now let us try to get into some details about the various complexity classes. Suppose we say O of 1, right? It's a constant. So what do we actually try to say there? What is the significance? What is the physical meaning of O of 1? So O of 1 means the operation, right, the algorithm doesn't depend on the size of its input. It's going to be constant always, irrespective of the size. So it does not depend on the size of the input. That is what is the physical meaning that we take. So what is O of n? We know that O of n is going to be linear. So the runtime complexity is going to be proportionate to the size of n. So as the size of n increases, it is going to increase in a linear fashion. That is a takeaway concept. Same way we can tell that logarithmic O of log n. Now this O of log n, normally it is associated with the algorithms that break a bigger problem into smaller chunks and proceed with each of the chunks. Same way, the O of n log n, usually it is associated with the algorithm that breaks the problem into smaller chunks for each invocation and then takes the result of these chunks and then stitches them back together. Something like a divide and conquer approach. That is where the logarithmic complexity comes into play. Now in the next tutorial number 3, we will have some derivations about the asymptotic notations where we can see such recursions or a divide and conquer approach, and we can try to understand how the algorithm complexity scales up. Now one example of the quadratic is O of n square, which is in bubble sort. It comes in the kind of sorting. One example is sorting. Now the O of n cube or O of 2 power n, 2 to the n, exponential, or they are in fact rare. Let's see why they are rare. Because even if you have an algorithm that is of this complexity, it is not going to be of any practical use. We'll come to that conclusion in just a couple of minutes. So you can look at the graph there. The graph where y-axis is the time, the runtime complexity, time measurement, and x-axis is the input size, n. So you can see that the constant is going to lie on the bottom, and you can see the quadratic is what is on the top. The cubic and the exponential are not sketched here because, as I told you, that incurs quite a huge complexity value, most probably astronomically large value, so which is not going to be of any useful point in actually analyzing that. Let's move on. Now let us have a small visualization. Now the important point that is conveyed with this particular picture over here is order of g of n is going to be set of functions with smaller or same order of growth as g of n. So the idea is, if I say order of n square, the order of n square will automatically include my order of 1, order of n, O of 1, O of n, and O of n log n. Right? So when I say O of n will automatically include my O of 1. So it is something like a subset. So when I say that n square, as we know that n square is going to automatically include my n complexity. That is the idea here. Right? And please note that the algorithms are analyzed only for larger values of n. If you can recollect the graph that we had for the rate of growth, there is a point called as n naught. So any algorithm is basically analyzed in asymptotic fashion only greater than, for a value greater than n, the n value should be greater than n naught. So any value of n less than n naught is not at all considered there, and we don't characterize them with any asymptotic expressions or curves. So the two main the points that we take away from this particular slide is, one is any higher order complexity class will subsume the lower order complexity classes within itself. Point number 1. Point number 2 is the big O is only analyzed for the larger values of n. These are the two main concepts that we take away from this slide. So some example is what is given there of our order of 1, order of n, n log n, and n square. Right? So the idea here is order of n square will subsume order of n log n, and 1. Or O of n log n will subsume O of n, O of 1, and O of n will subsume O of 1. That is the idea that we take. So let's move ahead. So this particular slide is in fact obtained as a result of experimental analysis, right? Some experiments have been carried out. basically with some codes where we try to measure the complexity. So what you see there is the table on the top gives the f of n, and it just tries to project the algorithm complexity with increasing n. So you say that n equal to 4, 16, 256. Basically it is 2. As we say, it is binary. So 2 power 2, 2 power 4, 2 power 8, and then 2 power 10. N equal to the last value 1048,576, basically 1024 square, which is 2 power 20. So you can see that if f of n is going to be 1, then you can see that as n increases, finally it is going to be only constant. There is no change, because we know that O of 1 means it's constant complexity, and the physical meaning is the complexity of the algorithm does not depends upon the input size. Now just look at the fourth entry there, fourth row of the table, where you can see that if it is n, you can see that the complexity increases exactly same as n. Right? It just increases with respect to n. Okay. Now the same way you can analyze, but which is more alarming is look at the last row, 2 power n, which is exponential complexity. Suppose we say that some algorithm is exponential complexity, which means that please forget that algorithm. Because you see here like 2 power n, you can see that if it is n is 2 power 20, then for that the complexity is 6.74 into 10 power, very, very, very huge value. Now suppose if you assume that you have a processor, you have a computer, you have a machine which can execute million instructions per second. That's what we abbreviate as MIPS, acronym MIPS. So if I assume million instructions per second, then how much time does the computer or the machine take to complete these set of operations? That is what is the table, the second table on the bottom. So here you can see that if it is million instructions per second, then for one instruction I take roughly 1 microsecond. That's why my first row, you can see that if it is O of 1, always it takes only O of 1, so 1 microsecond complete the operation. When I say it is O of n, then I can see that there it is 4 microseconds, 16, 256, it goes on increasing. Finally it comes to 1 second. Now look at the last row again, even the last but one, the cubic. I told you cubic and exponential are in fact very, very rare. So when you look into the cubic complexity, you can see that for n equal to 1024, slightly it's okay, 17.9 minutes. But as it goes say n equal to 2 power 20, you can see that it is 36,559 years to complete the operation on a machine that takes up million instructions per second. Now roughly if you want to really correlate the million instructions per second into a processor, you can tell that it is going to be say 1 megahertz processor. Now in fact when you say if it is going to be 1 gigahertz processor, then maybe you can divide it by 1000. Even then you can look at the last but one row of the second table. It should be by 1000 will give you 36 years, which is anyway quite large, right? So that is how the actual implication. So this is the physical implication about your big O notation. So this gives you a comment. Please note that we have actually ignored all the constants or the any other factors, lower factors. So in case if it was 10 into n power 4, we have just taken n power 4 into the picture for the complexity class. So this is the real implication about the big O notation. So if I have an algorithm of big O complexity, now roughly I know how much time does it take to execute. You can see that the first say 5 rows, the first 5 rows of the second table, which means order of O of 1 log n, log n, n log n, right? So that is what is actually tolerable. That is what is actually feasible. Because even for n equal to 2 power 20, it takes 21 seconds. But n square, which is quadratic, seems to be higher. But okay, I may try to manage it with the help of my processors, going for multiple core of processors, going for a higher speed of processors. But still, n square is not that much preferred. But the first 5 classes is what your algorithm should be. So in case now you develop an algorithm, then please analyze the complexity class unless and until it falls in the first 5 categories of the complexity class in big O notation. The algorithm is not going to be used by anybody. right? So that's the takeaway concepts on this slide. So let's move on. Now this slide, what we present is a kind of a statement wise, so the qualitative. So roughly, now what it gives is, if I have my f of n and if roughly the problem size doubles, what is going to be the implication? So if it is O of 1, I know it's going to be the same. So even if it is log n, the second entry, even in that case, it is going to be almost the same. So log n, then I can tell that if the problem size doubles, roughly it is going to be slightly above 1. So log 2, which is 1 point whatever is the value, right? Now what is n? If it is O of n, then if the problem size doubles, then I know that my complexity class is going to be double. The same way, right? So for square, cube and exponential, you can actually try to understand what is a qualitative statement. Now what is the final takeaway point is, a function g belongs to the complexity class if there is a number n naught and a constant c, such that for all n greater than n naught, we will have g of n less than or equal to c into f of n. So this was the definition for the big O notation that we had in the earlier lectures. We're just reiterating it. So we say that the function g is going to be eventually smaller than the function c into n. Right, and what you have there is the complexity classes. O of 1 will be a kind of subset of O log n, which is going to be a subset of O log n, and so on. We have your O of n square subset of n cube, which is going to be eventually a subset of exponential complexity. So this is what we have about the physical implication, the visualization, the actual implication, the geometric meaning or the physical implication of the big O notation. So once you analyze a big O notation, then you will be in a position to really comment about algorithm. Is it really practically feasible to use the algorithm or not? That will be the concluding statement. Now, the biggest asset that the big O notation gives us is, it allows us to essentially discard things like the hardware, the machine independent, the computer dependent sources, right? It is going to be ignored. There is no question of the hardware, right? Because we know that the complexity is going to be like this. Whether I use this hardware or that hardware, my big O notation is not going to be changing, right? But if I use another hardware, I will be able to assess what is my complexity. But the big O notation, when you compute the complexity class, that expression, that function is not going to depend upon the hardware components. Now let us have an example. In case if you have two sorting algorithms, right? Basically sorting is, you may either arrange it in one fashion, order, increasing or decreasing some way. Suppose if you have two sorting algorithms, one with a quadratic runtime and another with logarithmic runtime, right? We know that the logarithmic complexity class is going to be a smaller one compared to the quadratic one. So always the logarithmic algorithm will be faster than the quadratic one, right? Now this can be compared only when the number of input size grows sufficiently, because if it is below that, we may feel like logarithmic is slower than the quadratic, right? Now please note, this applies, that is the logarithmic algorithm will be faster than a quadratic. This applies even if the former is ran on a machine that is far faster than the latter. Why is it so? Because the big O notation isolates a key factor in the algorithm analysis, which is called as a growth. The big O notation neatly isolates the growth, the rate of growth, and presents that to us. So when the value of n becomes large, irrespective of the machine that's going to be used, the logarithmic algorithm will run faster than a quadratic algorithm. Now please don't test it for a size of 2 or 3, right? It should be sufficiently for a value greater than n naught. Now practically speaking, just a value closer to the n naught or closer value to n naught also practically may feel like both the algorithms are same, If you go for a sufficient value greater than n naught, only then the real essence of the complexity class will be visible, will be obvious. So that is about the big O notation. So in this lecture, what we have discussed is the real essence of big O notation. Practically, what is going to be the difference in terms of time, in terms of complexity. So out of the three notations, big O, omega and theta, we focused on big O notation. And please note, out of the big O notation, the complexity classes, the worst case or the maximum complexity class that one can actually experiment is the quadratic. Cubic and exponential is out of question. And quadratic is not actually preferred. You will have to go something less than quadratic like log n, log n, constant. Right? So that is the essence of this lecture. So with this we complete the series of lectures on algorithm and analysis. Hope to meet you in the next lecture. Thank you.